Okay, so let's get started. It's my pleasure to introduce Aditya Grover. He's assistant professor at UCLA. Started about 2 years ago, right? He's done some incredible work at the intersection of machine learning and climate. So we'll be talking mostly about ClimaX, which is a new paper I think all of us have read that he recently wrote. But his research actually goes, very, very broad in machine learning. He's done a lot of incredible work. He did his PhD at Stanford with Stefan Ehrman. Did a brief postdoc at UC Berkeley with Peter Abdil before starting his faculty job. Done a lot of work in generative modeling, both the theoretical side and the applications. When I was getting coffee with him this morning, he was telling me about some super interesting work about batteries, about using machine learning to optimize your battery, make sure your battery health is going to last a long time. So if you ever feel like your phone has been lasting a little bit longer, it's probably because of him. Yeah, so I think it's a great pleasure to have you here. Thanks for coming out, and looking forward to your talk very much.
Thanks, Carl, for the introduction, and thank you all for being here and having me present at Columbia. So, as Carl mentioned, I'm a computer scientist by training and have worked in a lot of AI disciplines, and all of them actually have the single mission to design agents which can operate in the real world and interact and reason just like humans do without too much supervision. And this research statement actually, if I had to force myself to put it into buckets, it happens to touch on 3 interests that my group focuses on. So the first is about learning with limited supervision. We are way beyond the era where we would have mechanical Turkers labeling and annotating data sets for us. And a large part of my research in the last decade has been trying to build some of the foundations around unsupervised learning, which enables us to get to highly data efficient systems. And now, beyond just training these systems for simple predictive tasks, I think about how their implications can be extended across time. And that brings us to thinking about how AI agents can make decisions in the real world and cater to different utilities that we might have. And to ground all of this research, I focus on traditional AI benchmarks as well as ground them in applications which I'm personally passionate about relating to climate and sustainability. During my PhD, a lot of that was about thinking about AI for designing better electric batteries. And since I've joined UCLA, I've been thinking a lot about the use of AI for weather and climate, which is what I'm going to talk about. And while all these 3 might seem distinct, I think the real magic happens when they intersect. And in fact, a lot of the work as mentioned today is at the intersection of unsupervised learning, coming face to face with climate and weather domains. When I used to give a talk like this, maybe to a very general audience 2 or 3 years ago, it used to take a lot of convincing to talk about what is generative models, why do we want to generate pretty pictures, and so on and forth. But today, this slide is the easiest of all. You say chat GPT and everybody's like, we get it. So that's what I'm going to do today. So we see a lot of these generative models all around us for language, speech, and vision. And clearly they've had an impact like no other AI technology. And so much so that often a broader category of these models goes under the name of foundation models. And if we look at what is so different between foundation models and the machine learning and statistics that we were used to almost many years ago, is that now, instead of training very specific models which go from some kind of annotated data set to a single task, we think about systems which are trained on a broad range of data and can be adapted to a broad range of tasks. So there is more general learning and there's more general inference happening with these AI systems. And this general purpose learning, ChatGPT being a very good example, allows us to then learn very, very rich models which can be used in so many different real world scenarios. And that's what is given this rise to this new term called foundation models. Now, behind a lot of foundation models, so like I said, it's not just ChatGPT. You're seeing that even in vision and speech and many other data modalities. But zooming out, we find that the same ingredients keep getting repeated across these foundation models. On the data side, we have to start looking at much, much broader sources of data, which represent a lot of diversity. With NLP, this was internet's data that was scraped from the internet, same for a lot of image models. And that represents a dramatic shift compared to the data sets that we were used to earlier. Now, on the modeling side, we have truly expanded what it means to be deep in deep learning. And now we are training massive neural networks on giant GPU clusters, which is also a hallmark of foundation models. And algorithmically, where a lot of the work has happened, has also gone from a single end-to-end training on one task to more like a two-step procedure, where the first stage is trying to do a lot of unsupervised learning with no one goal in mind, but trying to learn representations essentially, which are broadly useful. And then the second step is where the heavy lifting that was done in pre-training gets more customized through a lightweight fine-tuning procedure for the specific application that you care about. And these ingredients, and specifically this two-step recipe, has been applied again and again across a lot of AI domains in the last few years, but mostly relating to language and vision. So the natural question that I hope this talk inspires us to think about is, can we emulate this kind of recipe outside of language and vision? And specifically, my group has tried to make this attempt in the context of weather and climate. So I would say before we think about data-driven foundation models, weather and climate, in fact, already had a very general purpose model, which are the global climate models, which are often used in different forms for weather and climate predictions. And these are essentially physical models that are simulating some kind of equations governing how matter and energy flow from different systems, Earth systems. And this technology has been very powerful. It's also been improving at steady rates over the years, and has given rise to such wonderful forecasts that all of us use in our day-to-day lives. But there's also some very fundamental limitations about these. Physical knowledge is incomplete, especially when we go to very fine resolutions. It's very hard to describe a lot of subgrid processes with just physics. These models have been the luxury of only a few labs and centers around the world which have supercomputer scale compute. And lastly, these models scale with compute, but not so much with data. And so all the data that we have been capturing through a lot of sensors in the last few decades, that's not being put to the best use if we're still sticking to these physical models. And AI naturally can help with all of these challenges. Machine learning is not explicitly baking in physical assumptions, although it can benefit significantly from having physics as part of the learning process. Machine learning training is expensive, but inference is cheap. And even when we say about machine learning training being expensive, it's still very cheap compared to what we see with supercomputer scale physical models being put to use traditionally. And lastly, with foundation models, one of the most key fact has been that they have been scaling very well with increase in both data and compute. So the large number of data sets that we have available for weather, we can actually put them to good use potentially for training machine learning-based foundation models. So we made a first attempt in this direction through this model called ClimaX, which stands for climate plus X. We call it a foundation model for both weather and climate, because as I described, we have tried to adapt this kind of model for different time scales concerning traditional prediction problems for both weather and climate domains. And this work was led by my PhD student Tung here, along with some excellent collaborators listed down here. And so let's look into what made ClimaX possible. And even before that, maybe let's try to get a better sense of what it can actually achieve in terms of the experiments we did. So it's a single AI model backbone, which has been adapted to multiple tasks. The first one being weather forecasting at a range of time scales. So with a lead time of 6 hours for nowcasting to more in the range of 4 weeks, where you have this boundary of weather and climate, thinking of subseasonal to seasonal predictions. We also applied it to spatial tasks. So it's in particular downscaling, where we have shown how this model can be actually really good for increasing the resolution of our inputs. And then finally, we have been thinking about very long time scales for which these models could be used, such as climate projections under different anthropogenic factors for the greenhouse gas emissions. So this is only a representative set, which we inferred to be quite useful to the weather and climate communities. But really, ClimaX is X can be any task which we can think depends on weather and climate. And in fact, one of the future work directions that we hope with these kinds of models is we start thinking of tasks that are relating to things like agriculture, things like even insurance, and a lot of these different kinds of domains which depend heavily on weather and climate information. Okay, so what made this model possible? And it's essentially the same 3 ingredients which I mentioned as highlights of any foundation model. So it's unsupervised pre-training, it's training the model in a flexible and scalable manner to work with this kind of data, have a pre-training and fine-tuning phase, and the fine-tuning phase had an objective of its own. So I'll go over each of these components in detail, but essentially this is how we can adopt a recipe that's worked wonders for language and vision and think about weather and climate domains. So let's start with the very first one, which is thinking about the data. Now, one natural source of data for pre-training is perhaps observational data sets that we collect with on-ground sensors. It's physically constrained because we have limited number of observational sensory capabilities, and we also have the constraints based on time at what frequency we can record these kinds of data. And that's in contrast with internet scale data sets, which can keep increasing as we get more and more people on the web, and are, in fact, even in absolute terms, much, much bigger in magnitude to just observational data sets for weather and climate. Then this naturally makes us think that can we turn to proxy data sets? So a lot of indirect measurements being collected through satellite and aircraft measurements. And indeed, there have been products developed from the weather and climate community that we know of, like reanalysis data sets, which actually try to use a lot of model simulations being corrected through observational data and some other indirect measurements through data assimilation. Beyond these data sets, one of the key observations we made in this work is that if we really want to build a general purpose model that works for both weather and climate domains, we need to think of significantly larger data sets. And that's when we started looking into climate model simulations, especially in CMIP6, as a very rich source of data. Now, CMIP6 is much, much larger than any of these reanalysis data sets like ERF5. And it has different physical groundings for much longer range of past time and future as well. And that is something which we could possibly also start thinking about as a rich source of data for training foundation models. And as a first demonstration in this work, we looked at 5 such models of this ensemble, which are listed here. And we integrated this kind of data and used it for pre-training. So this is just a quick summary of what all is included within these data sets. So as we can see that these data sets include a lot of different variables at different pressure levels. So broadly, the variables that are being covered relate to geopotential, the U and V components of the wind, temperature, and humidity. And one thing to note in this table is that there's no uniformity in what variables are being covered by each of these data sources. And that's something that we should not view as a problem, but instead think of an opportunity to design better architecture that can embrace this heterogeneity. And this is a larger thing that you will see in a lot of scientific domains where when we're trying to fuse multiple data sets, we will be encountering challenges in which the data sets will be quite non-uniform. So with this kind of non-uniformity, we have to next think about the next step, which is to design the model architecture. Now, the first intuition for weather and climate often leads us to think of it similar to images. And indeed, one base architecture one could think of is this architecture called VIT. So it stands for Vision Transformer. And T, the transformer, is the same T in ChatGPT. So it's a very powerful architecture that's done a lot of amazing things in terms of learning from large unlabeled data set. It scales quite well with data and compute. And one could think of vision being put in the same vein as how these transformer architectures work for language. So just like transformers convert, think of sentences as a sequence of words and then are trained to predict the next word in the sequence, you could break down an image into a sequence of patches and make predictions over those patches. So here is an example of how that could look like for weather and climate, where if you have gridded data sets representing these weather variables on a map, you could think of that as an image and then flatten it out into a sequence of patches that your model could process. So at the surface level, this looks like a problem that vision architectures can handle well. But there are some differences which we realized and innovated upon in this work, which is that climate and weather data, that's highly multimodal. So we saw that already when we were looking at these kinds of data sets. There are dozens of variables being included here. So this is in stark contrast to typical image data, which has only 3 channels. You can think of each channel as a separate modality for red, green, and blue. Whereas for climate, we have to handle highly multimodal data sets. So based on this difference, and the second difference, which I already pointed out, which is that a lot of these data sets that we are trying to fuse together are quite heterogeneous. In fact, they might also have different coverages potentially for future foundation models, some being global, some being regional. We have to think of an architecture which builds on VIT while acknowledging these differences. And that's what we ended up doing with this architecture called CliVIT. And it essentially makes 2 changes to the base VIT architecture. The first change it does is it thinks of every variable specifying its own image that you can then break down into a sequence of patches. So instead of thinking of red, green, blue combining to one natural image, temperature, pressure, or any of these variables at different levels specify different images. And this is important to embrace the heterogeneity that we have, that different data sets that we are combining will have different variables. And this allows us to then merge a lot of different regional and global data sets into one. And this is just an illustration of how that would look if you have a sequence of variables and then you break it down into a sequence of patches for each variable. But there's no free lunch here. If you do this kind of processing and you have dozens of variables, your sequence length will grow a lot. And that's problematic for architectures like transformers, which scale quadratically in their computation with respect to the sequence length. And with dozens of variables, that's quite a prohibitive increase in computational cost. So what we ended up doing is that after a few layers of processing these variables independently, we do a variable aggregation step where we try to compute a weighted averaging of the patches at the same location for different variables. So this figure illustrates this best. So if we have a sequence of patches for each variable, then we look at the patches at the same location and then try to figure out a weighting to combine them. And this brings back the sequence length down to what is more manageable with these kinds of models currently. So these were the two main differences, and turns out they have a significant impact in how well these models work and scale when you have these climate data sets which have dozens of variables. Okay, the last part about our model design was how do we train this data set, train this ClimaX architecture on these heterogeneous data sets? What's the learning objective? And here, the key observation is that any kind of predictive task for weather and climate has to do with some kind of spatio-temporal forecasting. And the part about flexibility is really at what scale we are trying to make these kinds of predictions. So if you think about spatial flexibility, you're thinking about the input and output maybe spanning different geographical coverages or maybe having different resolutions. And that's something which actually the ClimaX architecture gives you a lot of leeway, because you can think of different coverages as having different number of patches in the input and output, different resolutions. You can resolve that by interpolating them to a common base standard. And those are things that the base architecture actually provides us a lot of flexibility already. Temporal flexibility is something which is quite critical and not covered by a simple VIT architecture, which is the ability that we want to be able to predict at arbitrary lead times. And that's where the separation of weather and climate also relies. So weather dealing with very short lead times and climate dealing with very long and everything in between, which is subseasonal to seasonal time scales. And there are two modes of operation here. So most of prior work has focused on iterative forecasting, where you train your model to predict at a fixed lead time ahead. So let's call that delta t. And then if you wanted to make a prediction at longer lead time, you keep resimulating this model, the output of this model at delta t, feed that back as input to predict at 2 delta t, and keep doing that until you reach your target lead time. Now, while this approach in principle makes sense, in practice, it has two problems. One is the issue of compounding errors. So as you keep going to longer and longer lead times, iterative predictions will keep accumulating errors, and we don't know how severe those accumulation would be. It may not be linear. It could also actually oftentimes we've seen it become super linear, and that can really affect the accuracy of these models. The second problem is you need to simulate all the inputs. Why? Because the outputs at your first iteration becomes the inputs at the second timestamp. So even if you care about a single variable, let's say if you want to just predict temperature 72 hours ahead, you have to predict all the variables that you have in input at 6 hours, 12 hours, and so on and forth, which can be quite expensive and needless to do in these kinds of iterative forecasting regimes. The alternative that we explored in this work is randomized conditional forecasting. So instead of making delta t fixed we make that as part of our input, and we sample it randomly during training. So in our work, we looked at delta t to be sampled within the range of 6 hours to 1 week. Although this is something we can tune, and in fact, in recent ongoing work, we found that the gains can become much bigger if you tune it well. And once you have this lead time being randomized as part of your training, then your model essentially becomes a multitask model that can cater to multiple lead times. And depending on what delta t you give as the input during pre-training, that's what you would set as the target output and optimize the difference between your model's predictions and the target through something like the mean squared error. All right, so this actually finishes the main ingredients we wanted to build a model like ClimaX. And here's just recapping them in a more visual form. So we are using an architecture like Vision Transformer with attention. It has some differences to account for the unique nature of climate data, in particular treating each of these variables as separately, and then aggregating them eventually so that the sequence length does not blow up for the bulk of the computation. And our inputs can be represented as tensors of longitude, latitude, and number of channels. And we do this randomized forecasting where we'll sample some lead time, and based on that, we decide what the target should be to predict ahead, and simply optimize a regression loss between our prediction and the ground truth, such as the mean squared error. So with this kind of simplicity that was deliberate in design, we are hoping that we can give rise to very general purpose models. In fact, that's what we see in a lot of our empirical results, which I shall describe next. So for pre-training, as I mentioned, we used CMIP6 data sets. And the reason being these are quite expansive in their variables that they cover. And there are a lot of these data sets that you can easily get, publicly. And the fine-tuning will be task specific. And what we showed in this work is 5 different tasks. The first 2 are to do with weather forecasting. And then we try to increase the lead time to somewhere in between weather and climate for subseasonal to seasonal. And then we look at a couple of tasks solely for climate relating to downscaling or increasing the resolution, and for climate projections under different forcings. So let's look at some of these results. So global forecasting, we trained for all the historical data until 2015, validated in 2016, and then we're looking at tests for the next 2 years. So here is a summary of some of the major results. The more detailed results are in the paper. But here we are looking at comparisons between ClimaX and IFS, both of them operating at the same resolution of 1.4 degrees. On the x-axis for all these plots is the lead time, how far ahead in the future we are predicting. And the y-axis, the first row of plots is for the root mean square error, for which lower is better. And then the bottom panel is for the correlation coefficient, where higher is better. So we can see this blue curve. It closely matches the IFS predictions. And the IFS is what's under deployment for 7 to 10 days. And then afterwards, it has a much more smoother gradation until it reaches the climatology baseline at longer lead times. This is something which actually in ongoing work we have exceeded. So we have actually improved upon the IFS predictions as well for the innovations. But even at the time when we were doing this work, it was quite impressive to us that we can achieve accuracies that are quite competitive with IFS. This is something just to visualize what happens. So here we are looking at 3 different variables, temperature at 2 meters, temperature at 850, and then the U component of wind. The first column is the initial condition, the current time, and then the ground truth that we're trying to predict in the future. And the third column is the prediction of our model, and bias is just the difference between the ground truth and the prediction. And we can see as expected, as we go to longer time scales, our performance decreases, but this kind of degradation is already competitive with IFS, and it's working quite impressive to what we had originally hoped for. I said this is a foundation model, and no foundation model analysis is complete without looking at how scaling this model affects the performance. And so we did some of the analysis with respect to both the size of the data and the model. And here again, we're looking at 4 different variables. And for each variable, we're looking at how the root mean squared error decreases as we increase the size of the data set or the size of the model. So in each of these plots, on the x-axis is the size of the data set, and the y-axis is the y-axis is the RMSE, and the different legends are for different model sizes.
That's a super quick question. These error metrics are for like grid point, comparing grid point to grid point at a time step. So sort of from a maybe like weather perspective of the error.
Yes.
Not like the mean state comparing the mean state. It's more like point by point. Okay.
Yeah. And averaged over the full globe. Yeah. Okay, so we see 2 trends. The first trend being, of course, as we increase the data set size, we get much more reductions in performance. And what's also exciting to see is that we are also seeing corresponding increases in performance as we increase the size of the model. So to achieve the same level of error, we can use a bigger model and would need lesser amount of data to achieve that same level of error here. And again, this is just the beginning. In our ongoing works, we have now scaled this to 3x of the size of the models that we see here. So reaching models with almost 1 billion parameters, and we're still seeing improvements occurring with those models. Another axis of improvement in weather and climate data specifically is the resolution at which we are pre-training and fine-tuning. And here, with the compute we had, we could test for 1.4 degrees versus 5.6 degrees. And we confirm a result which actually is being seen even in other works in the community recently, is that improving the resolution gives you easy wins consistently across all variables and lead times. The latest models, which are trained on much giant clusters, are being trained at 0.25 degrees. And we hope that scaling this model to even that resolution is going to give us big wins. Moving on to the second task, we looked at regional forecasting. And here the motivation is that global models are generally at coarser resolution, but almost every country has their own regional models, which are much better in accuracy, and they're also sometimes at much better resolutions available. So really, if we want to think about deploying these models on ground, we have to think about how synergistic these models trained on global data sets are with more regional scale data sets. So here, we constructed the setup where the model was again pre-trained on CMIP6, but to show the flexibility, we fine-tuned it only on North America. And then we compare it against a lot of the other architectures, including PlyVIP, where we didn't have the pre-training step. And here, again, we can see that the use of ClimaX, where we actually are also changing the resolution in some cases during fine-tuning, improving upon it to reflect how regional models are much better resolution than the pre-training data sets. We find that these kinds of improvements do show up quite evidently across the variables when we look at ClimaX versus the other baselines. So these were some of the results on the forecasting side. Now talking about downscaling. So downscaling, the task here we considered was we had a source data sets which were at coarser resolution, and then we cared about trying to upsample them into maybe a different distribution at much finer resolution. In this case, it was ERA5 datasets at 1.4 degree resolution. And this is a very different task from what ClimaX was pre-trained on. So there's no forecasting in time here. But the same backbone is flexible enough to be adapted to this kind of spatial task. And comparing it with the state-of-the-art vision architecture, which do not have any pre-training incorporated, we achieved consistent improvements across the RMSC and the Pearsall correlation coefficients as well. Again, some qualitative results which illustrate how this model is working. Now, the first column is the low resolution input. And the second column is the one which is at high resolution with much more finer details. And that's what we want to predict. And what we are seeing in the third column is the downscaled prediction. It's not perfect, but this task is actually very challenging. So if you look at, let's say, the second row, there's almost no level of detail that can, for a human, tell us what the ground truth would look like. But if you look at the downscale prediction, it's quite good in many of these scenarios. So the last set of results I want to talk about showing the flexibility of ClimaX is climate projections. And here we looked at the climate bench, which was released by researchers last year. And here it's asking the question that what will be the value of some target variable given some forcing factor X, where the target variable would be in this benchmark were things relating to temperature and precipitation, whereas the forcing factors were 4 different greenhouse gases considered in this work. Now, what is something to be noted here is that none of these target variables or forcing factor was directly present in how we pre-trained our data. So these were unique to climate bench. So you're thinking about, can we have machine learning models where both the input and output during fine-tuning is totally different from what it was seeing during pre-training? So here we had to think about essentially cross-modal adaptation of these models where the modalities change. And we had some previous work which actually had studied this question broadly for adapting language models to non-language modalities. And that same approach helped us here, where essentially we think about freezing selective parameters inside the main backbone. And that freezing is done both in a way that prevents overfitting and is computationally efficient. In fact, the only number of parameters we need to fine-tune in this whole pipeline is 0.01% of the parameters. So with just this highly efficient fine-tuning, we're able to adapt ClimaX to a totally different set of input and output variables. And here are some of the summary results. So what we're seeing are 4 different target variables Y, and the climate bench paper had produced some baselines, which are what we have in the first 2 rows. And then we had our own set of ablation baselines. For example, the CliVIT architecture, which had no pre-training, the ClimaX, which fine-tuned everything, and the frozen approach that I described, which is more parameter efficient and prevents overfitting. And we can see with this kind of frozen adaptation approach, again, we perform quite well on the temperature variables. We are not the best on precipitation variables. We're second best. And part of this has to do with the fact that we didn't really have a lot of precipitation data in our pre-training. So this also points to one direction for future improvement of these foundation models, which is to have more diversity in the set of variables that we pick for pre-training. So this is majorly what I wanted to talk about with respect to ClimaX, which is a foundation model that we have shown to work across many different tasks in weather and climate. My group also went through this journey of getting into this space, being complete outsiders. And throughout this process, we learned a lot of different things. And we tried to essentially bring it all together in the form of software that we hope benefits the community. So we call it the Climate Learn library. And essentially, It's driven by this idea that if you think about how AI has helped science in ways that have worked wonders, for example, things like AlphaFold, there is this element of rigor, reproducibility, and benchmarking, which is very, very key to making sure that we're on the right track. And this is a growing trend in the atmospheric sciences community as well, for good. But of course, there have been many years where we have read so many papers which are using very different splits of data sets, have very different evaluation metrics, and are actually comparing apples versus oranges, making it hard for the field to progress more faster. So what does ClimateLearn do? It's an open source PyTorch library, which has all these tasks that I described, and we're adding more. So weather and climate related tasks. It provides easy access to all the data sets I mentioned and more. It allows you to pre-process them with very simple utilities. And it provides access to many baselines that you can then build upon and evaluate them with a range of different metrics. And yeah, these are my students who worked on this project, and it's open source and under continuous development. So if you find it useful, please also consider contributing to it. So in summary, I talked about ClimaX, which takes this vision that we have seen worked really good wonders for AI, allowing us to touch new frontiers in language and vision, but then really seeing that what enabled this is a general purpose recipe that works really well for even weather and climate data. And this is, as I say, just the first attempt at trying to adapt it to weather and climate. So all of these different steps, whether it is thinking about what data to use for pre-training, what kind of architecture to embrace this heterogeneity in the pre-training data, and what should even be our pre-training objective, our fine-tuning mechanism. These are all things that I'm sure all of us as a community can innovate upon in the coming years. And yes, and ClimateLearn is one of the PyTorch libraries, which provides everybody an easy access to both ClimaX and many other models in the community. With that, I'd like to end and take any more questions.
Okay, because you were looking in the back, so I didn't know if there was anything. Well, thank you, Aditya. This was amazing. I think when we actually were talking, then unfortunately I have to wrap. You were starting to tell me about uncertainties, and this is just something, I was wondering if this is something you're planning to incorporate in your model. How would that work? Is this on your mind?
Yeah, that's a great question. In fact, I would say this is actually the #1 question we get from talking to weather and climate scientists. Where is uncertainty in this picture? And I would say, so we are working on it, and we are working on it more from a sense of generative models being efficient ways to quantify stochasticity when your output space is high dimensional, which is the case for global predictions of weather and climate. And I feel there's also quite a bit of room for even climate scientists to contribute to this question, because my understanding from a lot of these interactions is there are very well established ways in the climate community to quantify uncertainty. There are many good ways, even in deep learning, having developed for quantifying uncertainty. And they are not a one-to-one match. So I definitely think that reasoning through what of these mechanisms are synergistic and can be combined to give more calibrated uncertainties with better confidence intervals is quite a promising work. And actually, just to learn from Pierre, he has some good work in that's in the space of climate projections, trying to shrink the uncertainties from conventional models. So I'm pretty sure there's a lot of interesting future work we'll also see in that space.
Thanks. Great talk, fascinating work. With the LLM explosion, I think one of the most interesting features to see has been like all the creative uses of the embeddings, right? And now we have this whole, categories of tools that just deal with these, vectors produced by the LLMs. So I'm curious, how much have you explored, like, presumably you have a similar, embedding space for ClimaX, right? So how have you explored that space, and do you understand what the embeddings mean, and can you use them to do things like similarity search between different states of the climate system? I think you see where I'm going, right?
Yes, so we have visualized the embeddings, and what is an open question right now is what are those creative applications which in the weather and climate space where retrieval is of interest. And I mean, sure, like maybe one natural extension is like, oh, if there's like in search itself, right? Like if you want to customize search, we can use weather and climate embeddings as one additional source to customize search of queries. But I think more directly, I feel like a lot of those applications will be in sister disciplines, like maybe in agriculture and other disciplines, which can utilize weather and climate information in addition to so many other things that they themselves typically use to predict things like crop yields. And in those kinds of spaces, starting with just a weather and climate model might be an overkill, but having these embeddings being produced by these models, aiding the development of those models is something which I feel could be a very promising synergy between the two.
I have a question related to the pretraining. So you are using, there are different models, right? In order for the AI to understand and to know which data are similar, how do you apply your pre-training? So the AI will know, okay, these are the data that are comparable. So then you can predict, like having a benchmark.
Yes, for now, we are not explicitly adding identifiers which tell you which data set this model is coming from. And the reason being that if at fine tuning, we have a new source of data, it would have an identifier which was never exposed to the model during pre-training. But if it so happens to be the case that the set of data sets we're using for pre-training and fine-tuning come from the same source, in that case, having this identifier information can allow us to make these conclusions more explicit at a data set level, which is how similar are two different members of the climate, of the CMIP ensemble.
When you are saying same source, which source are you using? Which source?
So source I'm referring to is, if we go back, here. So here I'm thinking of, let's say, these 5 different CMIP rollouts as 5 different sources of data. And what we're essentially doing while pre-training is fusing all of them to be fusing all of them and asking a single model to perform forecasting for all of them. So in a way, it's learning a multimodal distribution where each mode in some space can refer to having approximated the physics that led to each of these 5 different data sets.
And later on, you can add more parameters.
Yes. So that's the flexibility that we want to keep, that during fine tuning, if you have your own version of CMIP or any other data set, you can include it here.
And maybe AI can find a parameter that doesn't exist, so it will.
Sorry, say that again?
Maybe the AI can find a risk parameter, a risk value that it doesn't exist. So it will add something new.
Yes, I think if we can,
After.
Yeah, maybe one way to do data selection during fine tuning could be exactly saying where all of these models during pre-training, if you look at their joint predictions on some target data set, where they are the most strong, and that can inform how to procure new data sets for fine tuning.
Yeah, because this was my initial question. Or pre-training is very important
Yes.
because you teach the AI how to think. So it has to know how to compare and
Yeah, I totally agree. In fact, one thing I would say, which I briefly mentioned during the talk as well, the choice of these 5 was purely driven by what variables we were trying to benchmark based on earlier work. But there's so many more streaming data sets. And if you want a more holistic picture of different Earth systems, we need to carefully think about what all data sets you want to include in pre-training, because that will determine a lot of what we see in terms of where the model works and where it does not work.
yeah, because in order to compare something, you have to know that the values are comparable.
Maybe we can take a question offline. I want to make sure we have a bunch of questions on Zoom too. I want to make sure we have.
And I also wanted to encourage early career scientists to speak out. Like if they have any questions, there are no bad questions, so feel free to speak. And in the meantime, we can read the questions online, and you can think about your questions. And even clarification questions are actually fine. Yeah. I just read the questions, and then I'll get back to Caitlin. There's the first question, which is on. Can you actually use ClimaX for distributions, and not just the means, and say for extreme events?
Yes, so we can definitely use it for extreme events. What the model does not do right now is give an uncertainty. And that has a fix that's easy, but not maybe the best fix, which is to have not just the mean prediction, but also variance being predicted. But there are more advanced methods in the machine learning community that now we're trying to integrate, like generative AI that I mentioned, to better quantify that uncertainty.
Thanks. And there's a second question, which is related to mention about the fact that you have such a large scale model. So the question is, how do you actually improve those models and the performance of those models once you train them, and when you have such a large number of parameters? So how do you actually fine tune that in a sense?
Right. And I think right now this model had somewhere in the order of 200 million parameters, which, while it sounds big, is actually quite small compared to language models. The smallest acceptable language model in academia today is 7 billion parameters. So we can still fine tune these models as a whole. But I did point to some evidence that there might be domains which for which we might want to be more clever about what we fine tune. So these were these experiments on climate projections that we had, where we essentially freeze all the attention parameters and then focus on the input and output embeddings and the layer normalization parameters, which are very few in number compared to the overall size of the model. And just tuning these parameters actually gives us more resistance to overfitting and actually computational efficiency at the same time.
I agree. Very interesting. I'm wondering, when you were showing those comparisons of ClimaX to the IFS model, were you running ClimaX with like single? You had a bunch of different lead times. Were you only running one projection for ClimaX, or were there some of those that were sequential?
Yes, it was sequential. So the question is here, when we have to select the target lead time, we have actually two approaches. One is you could just specify it as input and a single shot get the prediction. And that's what we actually used here. But you could also have done what you were suggesting, which is predict 6 hours ahead and then just keep repeating that process again and again. We have an ablation of that in the paper. This approach was performing slightly better, so that's what we used eventually.
Hi, thanks so much for a great talk. So if I understand it correctly, so you pre-train on CMAP, and then in some case you fine-tune on coarse grain error bar, and then that you use that to down the scale and come up with regional prediction. I wonder, like, if you have also considered the strategy of using high resolution aerofile to fine tune your model and predict it better for like regional scale.
Yes, I think what you're suggesting is what is the most deployable strategy, in fact. So we actually, those experiments I talked about were two separate experiments. The regional one was for forecasting, and then the downscaling was a separate task. Now, the trade-off is naturally that we were doing global downscaling. So, which naturally means that our outputs at higher resolution were already too computationally expensive for us to fine-tune on. But I think there's also work by researchers very recently where they take a global forecasting and then fine-tune it on very high resolution regional data set for Taiwan. And it works really well at even kilometer scale resolution. So I think that's a promising direction.
Okay, great. We have time for one more question.
Luckily, it's one question. Yeah, I just have a question. You use the leading time as one of the inputs, and my question is related, like, does it, so like, is it related with the training time step too? And another question is, like, if you, I just wonder when you, for example, when you predict the climate projection and when you do regional forecasting, do you like use output the data at the same time step, or the output for climate projection is like monthly output and then forecast is daily forecast? I just don't want to ask, like, the leading time input, what's the magic of this input, and when you do the projection and whether forecast, is that the same output time step?
Yeah, so the questions about the lead times. So how does it vary during pre-training and fine-tuning, essentially? So during pre-training, we don't know what the model will be used for at what time scale. So we randomize the input, and based on the randomization, even the target output during pre-training changes. But when it comes to inference, at that time, we have a specific lead time we care about, and that's what a lot of the x-axis in the plot says. So during evaluation, we set that specific lead time and see how does our model's predictions compare against those during pre-training. Compare those against the ground truth, my bad.
Okay, thanks so much, Aditya. Let's go one more hand. Thank you.